Hey man, this is actually my second take at this video because I realized the first one was way too long and overcomplicating it and kind of messy. So we're gonna go through it again, right? If this didn't make it clear enough for you, why does that sound so mean? I didn't mean that. I'm sorry. If this didn't make it clear, this is in fact a textbook question, and it's from chapter 13. I'd recommend trying it yourself first and then coming back to this video if you didn't understand it. Or actually just watch the video, who cares, right? There's another question just like this. There's two actually just like this, or three, I forgot. They're all basically the same. So yeah, you can just watch this one, practice the others, whatever. So first thing with this problem is I want you to actually understand what these words mean. And I'm sure you know, but I'm gonna say just in case you don't know one of them, right? So lattice energy is the energy it it describes the energy for when two gaseous ions combine to form a solid, and the ion part is kind of important. Ionization energy is yeah, you know this, the energy needed to remove an electron from an atom. Electron affinity, the energy needed to add an electron to an atom. Bond enthalpy is the energy you need to break a bond or destroy a bond, and the energy of sublimation is when a solid directly turns into a gas. So it like skips the liquid phase, for example, right? So say you have I don't know, you have magnesium, not gas, solid. It turns into magnesium gas, and if you notice, it didn't go to a liquid first. There was no intermediate step. It just kind of did it. That's how sublimation is. And another thing to understand about this problem, other than the definitions of the words that we're using, is that every single number here, all it's doing is that it's just representing a step. So you can think of it like step 1, step 2, step 3, step 4, step 5. There's no real order to this. You could do it in whatever order you want. This is just what I find to be the easiest, and this is how they're probably going to give it to you on the exam, so just learn it like this, or however you want. All I'm saying is forget that fucking colossal diagram that Warren likes to draw, which might be more useful for later courses, but for this one, I don't want to think about it. Yeah, so let's start, I guess. Yeah, each of these represents a step of a reaction which will all eventually combine to give you this final reaction, right? It's actually kind of like when you're balancing your reactions in like acidic and basic solutions, like you add everything up, or you make all the changes you need to, and then you add it up, you combine, and then everything cancels out and whatever to get you the final reaction. It's kind of like that. So let's start. What was our lattice energy? It describes the energy for when two gaseous ions combine to form a solid, right? Now it's not explicitly said, but it's pretty obvious. Your potassium is going to be a positive ion, and your chlorine is going to be a negative ion, right? So how you would draw that is you would do gaseous potassium, because you remember what lattice energy was? Gaseous ions, right? That and the chlorine combine to give you this. That's your first step done, right? Your second step, ionization energy. What was that? The energy needed to remove an electron from an atom. Now, which one of these guys has to have an electron removed from them? That's a very bad way to phrase that question, but it's going to be this guy. So how you're going to draw that is you're just going to draw how it was before it turned into an ion, or a cation, I should say. Am I stupid? No, never mind. And then you're going to draw it how it is now, if that makes sense. You should watch OChem, this version of this. It probably makes more sense. Electron affinity. Which of these two ions needs to gain an electron? Well, not ions, I should say, like their original atom states. It's the chlorine. So how are you going to draw that? is it's just going to be this, not that. Your chlorine atom is going to gain an electron and become a chlorine ion. That's that. Now, what about your bond enthalpy? Right, if you remember what bond enthalpy was, it was described the energy needed to break a bond, right? So I wonder, does the question actually tell you what that bond enthalpy is for, or do you like need to kind of figure it out? Let me check something real quick. What was this? 39? Does it tell you? Yeah. Yeah, bond enthalpy of Cl2. You don't need to figure that out, it'll tell you. Oh, it'll actually tell that for both of these. Yeah, you don't really need to figure that out, it'll tell you, but at least now you know, right? So your bond enthalpy for Cl2. What that means is you just need to write out the reaction for the Cl2 destroying, or the bond breaking apart, right? So how you would draw that is you would say your Cl2, they have some internal problems, like maybe a divorce or something, right? And then they just break apart. Now they're two separate guys. No, it's 2024. Energy of sublimation, if you remember what that was just when a solid directly turns into a gas, meaning it skips the liquid phase, right? And again, it'll tell you in the question, but you can also just figure it out by looking at your original reaction. Do you think the potassium would turn? Do you think there would be a step for the potassium to turn from a solid into a gas, or the chlorine from solid into a gas? And my logic on this would be that if this is a gas, why would it need to turn into a gas again, right? This is a solid, so yeah, that kind of needs to do that to, for this to happen. So yeah, how you're gonna draw that out is how I did it originally with that magnesium in the beginning, if you remember. You're literally just gonna draw your potassium solid turning into a potassium gas, right? Now you wanna start canceling stuff out to get a final reaction, right? So let's do that. Starting from the top, this potassium ion is going to cancel with this potassium ion. This chlorine ion is going to cancel with this chlorine ion. This electron with this electron. This potassium gas with this potassium gas. And here's where it gets a little weird. This is actually really the only part of this problem where you need to think about what's happening. I want you to notice that there's a 1/2 chlorine here. No such thing is on this side. And if you were to cancel these, or actually let me draw it a little more clearly. If you were to cancel these out, you wouldn't really end up with this top reaction here, right? So what would you need to change between these reactions to get this 1/2 chlorine and for everything to cancel out to get this final reaction? Think about that for a second. Your second's up. All you're gonna do is you're gonna multiply this reaction by 1/2. And if you got that on your own, you don't need me for anything. That's literally it. Because once you do that, there will be a 1/2 here. That'll get canceled out with that too. So that and that will cancel out. So now all you're gonna be left with is your potassium solid, your 1/2 Cl2 gas, turning into KCl. And if you want to make that more clear of what's left, this, and this. These are what's left. And yeah, to calculate the delta H, all you would need to do is show whatever happened here mathematically using these numbers. That's how I like to think about it. So all you're gonna do is say that delta H equals whatever we did to these numbers, right? So what did we do to the lattice energy? Did we do anything in that step? Nothing. We did nothing, so we're just gonna leave it as is, which is just that number. Did we do anything to the ionization energy step? No. So we're just gonna leave it as is. Did we do anything to the electron affinity step? No, so we're just gonna leave it as is. And did we do anything for the bond enthalpy step? We did. We multiplied the reaction by 1/2, or I guess you divided it by 2 if you want to say it right. So we need to divide this by 2, because if you remember what I said before, whatever is happening here is just a representation of this, or vice versa, depending on how you want to think about it. So you're just going to divide this number by 2, your bond enthalpy number by 2. And did we do anything for this step? We did nothing. So you're just going to do that. And if I remember correctly, this is 410.5 kilojoules per mole, which with sig figs is negative 410 joules per mole, kilojoules per mole, sorry. That's it. If you want to take a photo, there you go. Not much else to say. If you got questions, let me know. I probably overcomplicated that way more than it needed to be. Watch the OChem version. That's my advice.